Cloud. Very good. Okay. So Ethan Siegel, a very brief introduction, is an astrophysicist and a science communicator. He has published 6 books. I'm only familiar with the first two, Technology and Beyond the Galaxy. I hear you also have a Grand Cosmic Story and Infinite Cosmos, plus two two more that I don't remember the title. Um, and he's the creator of the podcast Starts with a Bang. If you want to know more, you go to lasertalks.com and you will find a link to his website and you will find out everything about him. Without further ado, the podium is yours.
All right. Thank you very much, Piero. And thank you to everyone attending the Laser Talks. It's exciting to be here. And thank you for inviting me to speak about the fundamental constants behind our universe. Now, when we think about our universe and we think about what is fundamental, we normally say, okay, we're going to reduce nature down to its smallest, most fundamental, most indivisible elementary elements. And that usually brings us right to the standard model, where we think, okay, like if I take matter and I take it apart and I go inside, 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 what can I create? And you find that there are quarks, and you find that there are leptons, and you find that there are bosons like the photon, which mediates the electromagnetic force, and the W and Z bosons, which mediate the weak nuclear force, and the gluons that mediate the strong nuclear force. And probably at some level, there's something that mediates gravity. Maybe there's a graviton, or classically, at least, there's big G, the gravitational constant in Einstein's relativity, plus there's the Higgs boson. And you think those are the fundamental entities that make up our universe, plus, whatever dark matter and dark energy are, plus if there's anything else we haven't discovered yet. So if it comes to the fundamental constants, what we say are, okay, you should tell me what a fundamental constant is. And usually when we say fundamental constants, we say, oh, that's right, we're talking about we're talking about elementary things like what's the elementary charge, and what is Planck's constant, and what are the Bohr magneton, what's a nuclear magneton. You think of all of these different constants, but what these constants are all about is they are about describing nature. They are about describing the particles that exist in the universe and the interactions that those particles experience with one another within this universe. And so you say, well, if I want to know what those are, what are the fundamental particles and their interactions, and how do the constants in the universe dictate what rules the universe follows, what the strength of various things are? And so you say, well, if we talk about particles, we might want to know what sorts of properties do interacting particles actually have with one another. And so maybe you can think of something like a pion, and a pion can be made if you have a pi minus of an anti-up and a down quark, or a pi plus is an up and an anti-down quark. And you say, well, that's an unstable configuration, and virtually they will emit a W boson and decay to a muon and a muon neutrino, or an anti-muon and a muon neutrino, muon and an anti-muon neutrino, or a muon or a positive muon and a muon neutrino. And then those muons will further decay through the weak interaction into a mu neutrino or antineutrino, an electron antineutrino, and an electron neutrino, or an electron or a positron. And you say, great, there are ways that these things decay. There are branching ratios, there are probabilities. And so if I want to know these things that interact, whether they make a stable thing or an unstable thing, what properties do they have? And you can immediately come up with a list of properties in your mind. You say, oh, yeah, They can have a mass. They can have an electric charge. They can have a spin. If they're unstable, they can have a mean lifetime. If they're leptons, they can have a lepton number. If they're baryons, they can have a baryon number. If they interact through the weak interaction, they can have a weak hypercharge and a weak isospin. If they interact through the strong nuclear interaction, they have to have a color charge. And there's a whole lot more. But all of these properties, I get bothered when we talk about those as being the fundamental constants because all of those properties have units attached to them. You measure mass, you can do it in electron volts, or you can do it in or you can do it in kilograms, or you can do it in, whatever you want, but it has units to it. And units are arbitrary. If I choose a different unit to measure something in, then I'm going to have a different number associated with it. And so you can ask yourself, well, if I don't like these units, is there some unit-free way that we can describe the universe's fundamental constants in? So, for example, instead of using the gravitational constant and the speed of light and Planck's constant, all of which have units associated with them, you can say, well, what if we used dimensional couplings? No, sorry, dimensionless couplings instead, couplings that are just pure raw numbers. And it turns out there is a way to do this. You can absorb all of the units into the framework that tells you how the universe works. And you can say, and then we're going to describe it within that framework with a series of constants that should just be pure mathematical numbers. So you say, all right, well, what if I started by saying we know how these four fundamental forces works. We know how gravity works. We know how electromagnetism works. We know how the weak force works. And we know how the strong force works. Then how many constants would we need to describe the universe? You say, well, let's start with four. We'll start with the dimensionless fine structure constant, which dictates the strength of the electromagnetic force. And there's the strong coupling constant, which is the strength of the strong nuclear force, and the weak coupling constant, which is the strength of the weak interaction. And we can even invent a gravitational coupling constant instead of Newton's big G. We can say there's a gravitational coupling constant. And I say, okay, that's great. And it's within the context of our standard model of particle physics and cosmology. But the standard model is messy. And by messy, I mean it has a variety of particles in it. And those particles come with a variety of properties that are unique to each individual species of particle. The top quark is different than the bottom quark, is the charm and the strange and the down and the up quarks. The Higgs boson is different than the Z or the W boson, or the quarks and the gluons, and the photons and the gluons. And you can have the leptons, and you have the tau and the muon and the electron, but you also have the tau neutrino and the muon neutrino and the electron neutrino. So if I want to say, well, we had these four coupling constants for the forces, what fundamental constants do we need to describe these particles of the standard model, the known particles that are in existence? And you say, well, what I want is if each of these particles has its own rest mass, how do I get that in the standard model? Well, the way you get a rest mass is you couple to the Higgs field. The Higgs field is what gives particles a non-zero rest mass. If you don't couple to the Higgs, you can be massless. So we don't need a fundamental constant for the photon or the gluon because they're massless. But everything else in the standard model has mass. You have 6 quarks, up, down, charm, strange, top, and bottom. And those 6 quarks have 6 different masses. So each massive quark needs its own dimensionless coupling constant to say how much it couples to the Higgs field. Same thing with the leptons. We have the electron, mu, and tau. And since the late 1990s, we've also known that the electron neutrino and the muon neutrino and the tau neutrino cannot be massless. They have small but non-zero rest masses. So now we need 6 more coupling constants, 6 more dimensionless couplings to the Higgs field to explain the masses of the leptons. And the W and Z bosons have mass. So we need 2 more coupling constants for each of them. And the Higgs boson has a mass. So we need a self-coupling from the Higgs boson to the Higgs field. Bonus, once we put these in, we discover that the weak coupling constant and the gravitational coupling constant are redundant. So we added 15 more to our original 4, but we got to take 2 away. So now we only have 17. But that's not the full story, because within the standard model, you also have what's known as quantum mixing, where particles that have the same quantum numbers can mix together to create these mixed states. In the quark sector, the quarks mix together in a way that we need 4 extra mixing elements. This is determined in particle physics by the CKM, or the Kabibo Kobayashi Masakawa mixing matrix. Whereas in the neutrino sector, we have the PMNS mixing matrix, the Pontecorvo, oh man, well, we'll just call it the PMNS mixing matrix. That also needs 4 extra elements to mix the 3 generations and an additional phase mixing angle. So then I say, all right, so now I went from just the 4 fundamental forces, I went up to 17 when I added in the masses, and then I have mixing, that's 8 more, that brings me up to 25. But our universe also has dark energy in it. And if I say, well, let's make dark energy the simplest thing it's allowed to be, and that's a cosmological constant, that's great. Then I only need 1 more fundamental constant, 2 independent force couplings plus the 15 Higgs couplings plus 8 mixing parameters, 4 for the quarks and 4 for the neutrinos, and 1 cosmological constant. That's 26 fundamental constants I need to describe the universe we have. And that still doesn't give us everything that we need. We're still missing baryogenesis. We know the universe has more matter than antimatter in it. They are not symmetric. How did it get there? Well, current physics can't account for that. You need some extra new physics, and new physics are probably going to mean a new coupling constant. For example, as illustrated here on the screen at right, you can see, well, I can add in, like in grand unified theories, we have these super heavy X and Y and anti-X and anti-Y bosons, and they would need to have their own masses and decay branching ratios, and they'd need constants associated with them to create this matter-antimatter asymmetry. What about cosmic inflation that preceded and set up the Big Bang, where instead of being filled with matter and radiation, the universe was filled with energy inherent to space itself? That probably brings new physics and, again, new constants along with it. What about dark matter? Well, if it's a massive particle, I need at least 1 more coupling constant, and that means 1 more fundamental constant. And why is there no strong CP violation, right? You can write it down. It's not forbidden in the standard model. Why don't we see it? Is there a fundamental constant associated with that? We don't know. So 26 is sort of the minimum conservative number of fundamental constants that we need, but it still doesn't even explain everything about the universe we observe. But assuming that there are maybe some more constants and we can explain everything, then you'd want to know, what is it that set these fundamental constants in the first place? Could they have been set in the early phases of cosmic history that created the universe as we know it, that resulted in the hot Big Bang occurring, that provided the seeds of cosmic structure that have grown into the great cosmic web we have before us today? Well, we have some early signals we can look at, and maybe that can help serve as a clue. Inflation back in the very early stages of the universe, you can think of similarly to how we think of the Higgs field, that you had some restored symmetry where the field energy itself was very large. But as the energy drops, or as this ball, as illustrated here, rolls down from the top of the hill into a valley, well, now a symmetry is broken. There's a preferred direction. There's a preferred location where the ball is. Instead of all directions looking the same, when you roll off the top of a hill, you can roll into a valley. You can roll into a low point. And maybe it was the act of that that set what the fundamental constants are. This is one idea that shows up in the context of the multiverse, right? In the context of string theory, you say there are all these different string vacua, and you have different minima that you can wind up in. And maybe in one minimum, you have a certain set of fundamental constants that dictate how the universe is. But maybe in a different minimum, you have different sets of fundamental constants that set what the universe is. And so, fine. But then you ask, well, I only live in one pocket of this multiverse. What determines what's in the other pockets? And so you add inflation and this idea of different vacua together, and you come to the inflationary multiverse, where you say, oh, you look, inflation occurred at some energy, and we inflated, and space grew and grew and grew. And then in one region of space, there was a quantum fluctuation that brought inflation to an end. And that resulted in a hot Big Bang that included our entire observable universe. And we can look at what we see in our observable universe, from the stars and galaxies that are nearby to ones at vast cosmic distances, to the leftover background of radiation that was created in the hot Big Bang. And you can say, well, what can I learn about inflation from looking at that? And is this consistent with the idea that, well, there are different pockets in the universe, if you go all the way up to Planck scale energies, that maybe the fundamental constants got set there? And so you would wonder, oh, are there different regions of the multiverse that have different fundamental constants? And can I learn something about them and access them? And it turns out that if you look at the cosmic microwave background, and in particular, what I show here is the polarization in the cosmic microwave background as measured by the Planck satellite, it turns out that is disfavored. The Planck scale, where allegedly string theory is important and gravity is comparable in strength to the other forces, and maybe, just maybe, the fundamental constants get set by something, that's up at the Planck scale at 10 to the 19 GeV of energy. But I learned from inflation and from the cosmic microwave background that there's a maximum energy scale that could have been reached during inflation. And it's more than a factor of 1,000 below the Planck scale. It's almost 4 orders of magnitude down for it. So if I need to be up at this high energy to set the fundamental constants, and inflation occurs at a lower energy than that, could the inflationary multiverse be responsible for our values of the fundamental constant? I won't say it's not possible, but it seems disfavored by the energy arguments we have. You would say, well, if it happened during, like, you had some type of symmetry breaking, maybe you would see the constants vary across space or across cosmic time. Well, people have looked for this. And when it comes to variations across cosmic time, people have claimed to see it, but it looks really constant. No variations in the fine structure constant or any other constant. What about across space? Well, we've looked for that too, and we don't see evidence for the constants varying in different directions in space. A man named John Webb and his team presented evidence for that back in 2008 or so, but it turned out that those were systematic errors with their data acquisition, and other groups went and were able to say, no, the constants don't vary down to a greater precision than Webb's uncertainties were. And that's kind of where we are today. In summary, we have at least 26 fundamental constants that are needed to explain the universe we have. And those 26 fundamental constants, when you take them all together, they still don't explain several major mysteries or puzzles that we have with the universe: baryogenesis, dark matter, cosmic inflation, and the strong CP problem. So even with those 26 constants, we don't have enough. What sets the constants? Was our universe just born this way? Was Lady Gaga right? Maybe. We don't know what set them. Could it be that the constants are different in different pockets of the inflationary multiverse? Well, we disfavored it based on energy arguments, but the truth is we don't know that either. The fundamental constants are kind of essential to our universe turning out the way it did, where stars shine and atoms form and link up to make complex molecules. This seems essential to our existence. And if the fundamental constants, you tweak them by too much, none of this would be possible. So, where are we? Well, this is up to the frontiers of what we know today. We know what the fundamental constants are, at least many of them. We know how they play a major role in setting what happens in our universe into motion. But as far as what sets the values of the constants and whether they're different in different pockets of the multiverse, and they could have been different here in our universe, we still don't know. And that's the limits of our scientific knowledge today. And I'll stop here to take questions. Thanks, everybody.
Yeah, it's kind of breathtaking when you hear the summary in 20 minutes. Anyway,
Well, this was the amount of time that
no,
some great advice I got as a grad student. Do the
yeah,
best job you can in the time you have to do
yeah,
it.
but it's even more powerful because in 20 minutes you really realize the mystery. This is really not just fundamental constants. This is the fundamental mystery. The fundamental constants are the fundamental mystery of the universe. Even why 26, or maybe there's some that we still have to discover, but why that number? So first of all, if anybody has question, please put them in the chat or in the QA. Myself, um, so you mentioned briefly that there's been discussion if the constants are really constant over time and over space. And I can't find the name of the Cambridge physicist that I heard a long time ago when my hair was still dark. And he was a skeptic. And of course, I don't remember the argument, and I don't remember his name. But that left me that thing in the back of my brain, we're really sure, that constants have always been what they are today, and that they are the same everywhere. If we could travel 100 million light years, it would still be the same speed of light. It would still be the same everything. So
Well, there are a lot of measurements we've acquired that allow us to place tremendous constraints on how much the constants are allowed to vary. For example, we can look at absorptive gas clouds at different redshifts, and that tells us how has the cosmic microwave background changed in temperature. And we find that, yes, it does follow that 1 plus z relationship, which rules out variations in many types of constants, including fine structure. We've looked at, Jörg Raffelt did some research on could some of the fundamental constants have varied as far back as we can see distant quasars? And the answer turns out to be that you can say that a wide variety of constants have not changed over 11 to 13 billion years of cosmic history. When you look at constraints from absorption lines on how much could the fine structure constants have changed, less than 1 part in a million over any direction you look in, and over, 98% of the history of the universe, which is far back as our most distant galaxies go. The one type of evolution we do see is that the strength of the couplings that we find, they don't vary in space or time, but they do vary in energy. at higher energies, for example, right now, if you say, what's the fine structure constant? A lot of people know that number 1 over 137, and it's 1 over 137.0359999, etc. But they say 1 over 137. But if we go up to the electroweak scale, up to energies that they get at, Fermilab's Tevatron and at the Large Hadron Collider in CERN, you say, well, now instead of 1 over 137, the strength of the electromagnetic coupling rises up to 1 over 128. And we know that all of the couplings, the strong, weak, and electromagnetic coupling, are in fact energy dependent. And people have used the fact that they seem to converge and almost kind of meet as evidence for, well, maybe that's a hint that some type of grand unification of forces happens at some high energies. Is that true? We don't know. Does this mean that the constants do vary over time because energy varies over time? Well, in a sense, but that's really only important in the very early universe. And that is, evolution that's predicted by the standard model. It doesn't change the value of the constants at our current energy. So that's kind of the limits of where we are based on what constraints we can place based on observations and experiments on constant variation today. But once you leave our observable universe, all bets are off. We've only ever observed or measured what's in our own. And physics at its core is always an experimental and observational science. And I say this as a theorist. So, as much as I love theory, you've got to confront your theory with reality.
Can you say a few words, if you have an opinion, on last year's widely publicized finding, the DAISY data that seem to show the dark energy may evolve over time, which could just mean that that's not Einstein's cosmological constant or something else. What's your take on that?
Well, I'm very curious about that, right? The DESI data is a hint that maybe something is wrong with our picture of the universe. And when they said we're gonna make our best fit to the data we have, they at almost 3 sigma or so, they say it's in tension with standard lambda CDM. But then you say, I want to take a look and see what you're getting in your best fit data. And their best fit data for the DESI data says, hey, look, we have this amount of matter density in the universe. And if you have this amount of matter density in the universe, then you have these sets of cosmological parameters, and you can only disfavor dark energy being a cosmological constant at almost 3 sigma. And then you say, well, hang on, I have other sets of observations too. I have cosmic microwave background data, and I have type 1a supernova data. And you say, what happens if I add them in with the DESI data? And if you add them in, the tension goes up, right? If you add the cosmic microwave background data with the DESI data, now it's more difficult to have constant dark energy. But that's also because the cosmic microwave background data favors a different value for the matter density of the universe than the DESI data, than the large scale structure data does. And they favor a different expansion rate today. And they favor a different contribution of neutrino masses to the data. And then you bring in the supernova data, and it turns out we have 3 different supernova samples we can use. We can use the Union data, we can use the Pantheon data, or we can use a third set of data that I forget their collaboration's name. And in 2 of those instances, the tension rises again, because whereas the CMB data predicts higher values of omega matter, the supernova data favors lower values of omega matter. And whereas the CMB data favors lower expansion rates, the supernova data favors higher expansion rates. So when you add all of these 3 data sets, the supernova and the CMB and the large scale structure data from DESI together, you find they're in tension. And where is that tension showing up? Well, it's in a few different places. It's in the matter density of the universe. It's in the expansion rate of the universe. It's in the sum of the neutrino masses in the universe, which, by the way, when you combine all three data sets, the most favored value for combined neutrino masses is negative. And that's a troublesome thing to me because that's an unphysical solution. And then you say, oh, yeah. And in addition to all of those things, the different dark matter density, the different expansion rate, the different neutrino masses, it also predicts different properties for dark energy. So if you say, well, I'm going to demand that we have one value for neutrino masses and one value for expansion rate and one value for the matter density, then the only place to put your variations is in the dark energy evolution. So when you combine all of that together, that's where the suggestion of dark energy evolution comes from. And I'm not saying I don't believe that dark energy could evolve, but I think that what we're seeing is that there is a tension between these three different types of data sets. And what it's going to take is superior data to figure out where is this tension coming from. Is it because the matter density is evolving? Is it because dark energy is evolving? Is it because neutrinos are doing something weird? Is it because there was some early species of energy that's decayed away? Is it because the expansion rate is evolving in some non-standard way? I think we're going to await DESI's final results because they've only released their, first and second year results. And I think their final results are going to have about 3 times as much data. And then after DESI, we're going to get more large scale structure data from space and ground based telescopes like SphereX, like Euclid, like Roman, and like the Vera Rubin Observatory. So, being that this is a data driven science, I want to see the data. And when more and better data is in, then I want to know what it's telling us, because there is a tension where everything doesn't add up. But based on the evidence we have today, on the strength of the evidence, I think it's premature to draw a conclusion that dark energy has to be the thing that's evolving.
Yeah, very interesting. Besides this, which of the in the last 5 years, what has been the most intriguing finding from your point of view for an astrophysicist?
For me, the most profound discoveries have come from the James Webb Space Telescope because it's taken us further back into the cosmic past than anything else has ever taken us. If I said in 2022, before the James Webb Space Telescope began science operation, what was the most distant galaxy we knew of? I would have said, oh, it's GNZ11. It was discovered by Hubble. We now know its light came to us from 420 million years after the Big Bang, when the universe was 3% of its current age. And, we would say that that's the most distant galaxy. And now that galaxy is not even in the top 10 of most distant galaxies. All 10 of the top 10 were discovered by JWST and measured by JWST. And we have found populations of early galaxies, the little red dot galaxies, galaxies that seem to have active galactic nuclei, maybe even with overmassive black holes, where some of them have black holes that are more massive than all the stars in the galaxy combined. I think this is really teaching us, hey, we're having a revolution in how structure formed in the earliest stages of cosmic history. To me, that's the biggest development, is we are seeing further back past the old frontiers of where our cosmic limits were, and it's showing us some surprises about the universe. And it's up to us, and we've also made tremendous progress on this front in determining how the universe did grow up to be the way we observe it to be. And so at those frontiers, I think fascinating things are happening. But on a more astronomical and non-cosmic things, we're also seeing details in stellar and planetary systems that we've never seen before. And that's another thing that JWST, ALMA, and new generations of observatories are going to continue to bring us.
Yeah.
Piero, I want to note that there is a question here in the Q&A that I see from David Schuler, who asks if I can recommend some resource to help him get his head around the idea of unitless constants. What's a source that'll be comprehensible to someone with only an undergraduate education? I'm actually going to recommend there was a book written maybe 5 or 6 years ago by a duo of physicists named Geraint Lewis and Luke Barnes, and the book was called A Fortunate Universe. And even if you only have an undergraduate education, and even if your major was not physics or astrophysics, A Fortunate Universe does an excellent job of breaking down what the different fundamental constants are, what they mean, and how much you could vary them and still get a universe where intelligent observers like humans could still possibly exist. And so I think that book gives an excellent treatment of that.
Okay, excellent. Well, thank you very much for your presentation, and thank you very much for this tip. And we'll keep following you on the web.
All right. Well, the universe is always going to be out there for us to explore and enjoy. And I look forward to the next opportunity I have to bring a little slice of it to all of you.
Okay, thank you, Ethan.
All right. Thank you very much. Have a great afternoon and evening. Bye bye.